Here we talk about the Lenz's law, which is actually the direction of the induced current. So this will be a bit complicated. So an induced current has a direction such that the magnetic field due to this induced current opposites the change in the magnetic flux that induce the current. The induced EMF has the same direction as the induced current. So here Lenz's law at work. As the magnet is moved toward the loop, the current is induced in the loop. The current produces its own magnetic field with blah blah blah. Okay. So here, let's see this figure. Okay, so here, suppose B is the external B field. B is the external B field. And B and D is the induced B field. So actually the case is like originally the B field is pointing downward. So in increasing the external B field induce a current with a field that opposite the direction. Which means that if it is pointing downward and this B field increase, then this loop will generate another B field to counter this change. But of course, the magnitude isn't necessarily the same with this one. The magnitude depends on the Faraday's law, and only the direction is related to the change. So if the external B field is pointing downward and it increase, then this loop will generate a B field pointing upward. And in this case, using the right-hand rule, you will know that the induced current is counterclockwise. Then this induced B field pointing upward. So the induced current creates this field trying to offset the change. And so you use the right-hand rule to determine the direction of the current. So the next case is decreasing the external field B induce a current with a field B induced that opposite the direction. For this case, B is increasing. But for this case, B is decreasing. In this case, B is decreasing, so this loop will generate a B field pointing downward to offset this change, because B is decreasing. So this loop will try to generate some B field pointing downward. In this case, you use the right-hand rule. You can determine that the current is clockwise. So we have a counterclockwise, and then here we have a clockwise. So for the next case, if B is pointing upward and is increasing, so this is increasing, then for this loop, it will try to generate a B field pointing downward, and using the right hand rule, you will know that this is clockwise. And yeah, so if B is decreasing, then this loop will try to generate a B induced pointing upward. And in this case, this is counterclockwise. So this is about the Lenz's law, how you determine the induced current. Rather than just looking at the external B field, you need to check how the B field is changing. So so this is how to determine the direction of the current. Any questions? Actually, not so straightforward, but this is how you determine the direction of the current. And actually, this is what this minus sign means. It depends on the rate of change of the magnetic flux, not the magnetic flux itself. Because when you just look at the direction of B, then it is not the same sign with this one. It depends on how it change. Which means if it is pointing downward and increasing, which is like if you just regard this direction is positive, then pointing downward increasing is just like decreasing, and pointing downward decreasing is just like increasing. So this is like pointing upward increasing is increasing, and then pointing upward decreasing is like decreasing. So this is you can consider like this. Okay, so let's see a sample problem. So a conducting loop consists of a half circle of radius small r and three strict sections. And three strict sections of this one, and this one. So the half circle lies in a uniform magnetic field that is directly out of the page. So the field magnitude is given by B equals this expression, with B in Tesla and T in seconds. An ideal battery with EMF EBAT equals 2 volt is connected to the loop. The resistance of the loop is 2 ohm. So what are the magnitude and direction of the EMF induced around the loop by the field at t equals 10 seconds? So So here first we try to consider the induced EMF by its magnitude. So we take the absolute value so that we can skip the direction first, skip the minus sign first. So it is like d dt b times a, because because b doesn't relate it to the position. B is uniform over this area, and it only related to time, so it doesn't relate it to the position. So the integration is just like the multiplication. So a doesn't change. The only changing variable is the time. So it is like a times d dt b. So a is a half circle. A is a half circle. So 1/2 pi r square, and then d dt, and then b is 4t squared plus 2t plus 3. So we can plug in r equals 0.2 square, and then we take the derivative of this polynomial, which is very easy. T square, take the derivative, is 2t, so it is 8t, and then plus 2. So now if we just evaluate this one at t equals 10 seconds, so it is like 1/2 pi 0.2 square, and then 8 times 10 plus 2. So this is 5.2 volt. 5.2 volt. So this is the magnitude, and actually we need to determine the direction. Actually, So as we can see here, the magnetic field is actually a positive number and also increasing, right? Also increasing, because you can see after you take the derivative, it is 80 plus 2, which means that the rate of change is positive when t is positive, which means that the electric flux here is increasing out of the page. So in this case, the induced B field should be into the page. Which means B induced should be into the page, which means that if you use a right hand rule, your thumb pointing into the page, then it should be clockwise. So the induced current is clockwise. Any questions? Okay, so for part B, what is the current in the loop at t equals 10 seconds? So for this case, originally we have the battery to be 2 volt, and then we have this loop like this. And as long as we have the induced current is clockwise, which means the EMF we just calculate is 5.2 volt. It's like 5.2 volt in this direction. So for the 2 volt, it is like the other way around. It is like in this direction. Because if you just ignore the EMF, the current should go counterclockwise. However, the EMF is clockwise. So in this case, the current at 10 seconds should be E net over R. R is the resistance of this loop, which is 2 ohm. So it is like EIND minus E battery over R. So it is like a 5.2 minus 2 volt over 2, which is 1.68. So any question regarding to this? Okay, so next we have another sample problem. Yeah, here here we have a rectangular loop of wire immersed in non-uniform and varying magnetic field. And varying magnetic field is perpendicular and directly into the page. So the field's magnitude is given by this one. So it is not only related to time but also related to the x-axis coordinate. So with b in Tesla, t in seconds, and x in meter. So the loop has width w equals 3 meter. W is the width, h is the height. What are the magnitude and direction of the induced EMF around the loop at t equals 0.1 second? 0.1 second. So first of all, we need to calculate the magnetic flux. So phi b is integration of b dot dA, of course, over this rectangle, which means x is from 0 to w and y from 0 to h. But hopefully, b doesn't relate it to y, so it will be a bit easier. So, and of course, we know b is perpendicular to this rectangle. So b dot dA is nothing but a BDA. So they're perpendicular to each other, and we may assume the positive direction to be into the page. So that dA is pointing into the page. So dA is like this area. And actually, we don't really need to integrate over dy because it doesn't relate to y. So dA is just like h times dx. So this is the the rectangle. We don't really need to further cut it into, we don't really need to cut it like this. If B is related to Y, then we probably need to do this procedure, so that this integration will be a double integration. We have something like dx dy, but now it is not related to Y, so we don't really need to cut it like this. So this whole dA is just like h times dx is this area. So we have integration of bh dx. Of course, x is integrate from 0 to w, 0 to w. So let's plug in b, and plug in all the values. So b is 4t square x, 4t square x square is b, and then h is 2 meter, and then dx, and then from 0 to w is 3 meter, 3 meter. So we just plug in everything, and then we only integrate for x, so we can just have 8t squared putting outside, and then we have x squared dx 0 to 3. So this one is nothing but x cubed over 3 evaluate from 0 to 3. So plug in 3 cubed is 27 over 3 is 9, and then 0 is 0, so we have a 72t squared. So this is 5b, which is just a function of time. So we can use the Faraday's law to find the d phi b dt, to find the electromotive force. So it is nothing but d dt of 72t squared. So it is nothing but 144t. And finally, what we need to find is E, evaluate at t equals 0.1 second. So it is 144 times 0.1, which is 14.4 volt. So this is the induced EMF. So this is the magnitude, and we need to determine the direction. So here, B is pointing into the page, and it is always positive, for t is a positive number. And of course, we know that this is also increasing. You can simply check that the phi b is increasing. You can simply imagine here, because if you plug in 1, it is 4x squared, and if it's plugged in 2, then it is 16x squared. So you can simply check that phi b is increasing with respect to time, which means that the B field is, the magnetic flux is increasing into the page. So the induced B field should be out of the page. Which means the induced current or EMF is counterclockwise by the right hand rule. You can simply check that. Any questions? Okay, so yeah, so next, here we talk about the energy transfer. So here we have a rectangle loop of wire with L, has one end in the uniform external magnetic field. So you can see this is the rectangular loop. In this area we have the uniform magnetic field pointing into the page. So here we have this field is maybe produced by a large electromagnetic outside. It's not shown here. So the dashed line in the figure shows the assumed limits of the magnetic field, and the fringe of the field at this edge is neglected. So we only assume there is a uniform B field inside this area and there is no B field outside. So you are to pull this loop to the right at a constant velocity v. So you suppose the shape of this loop won't change, and then you try to pull it out of the magnetic field. So yeah, so there will be some flux change, because you can simply imagine at this moment it will look like this, and at the next moment it will be look like so at the next moment, for the first moment, there may be 1, 2, 3, 4, 5 column, and later then there may be something like this, because V is pointing to the right side, so there will be less flux, because you will consider the flux is like B dot dA. So for this case, B doesn't change, but the A is decreasing. For this case, we consider this A, and for this case, the A is of course decreasing. So actually, phi B is also decreasing. So therefore, a magnetic field and a conducting loop are in a relative motion at speed v. Then so the flux is changing with time. And the weight of work to pull the loop at constant velocity v, you must apply a constant force to the loop, because the magnetic force of the equal magnitude but opposite direction act on the loop to opposite you. The rate at which you do work is that the power is then F times V. Yeah, here we have yes, you can imagine if you just try to pull the loop to the right side, which means the magnetic flux is decreasing. In this case, there will be the B induced pointing out of the page, due to the Faraday's law and also the Lenz's law. So we know that should be into the page, because the external B field is pointing into the page and it is increasing. So the B induced should be pointing into the page. Which means that the induced current should be clockwise. the induced current should be clockwise. And as you know in chapter 28, you know that the Coulomb's force, sorry, not the Coulomb force, the Lorentz force. And then the alternative version of the Lorentz force is FB equals I L cross B. So I suppose you remember, because this is for the test to midterm exam tomorrow. So so as long as we have a current going clockwise, going clockwise. So I is clockwise. So for the left wire, we have L pointing upward, I pointing upward. So I cross B, L cross B, L cross B. L has the same direction as the I, so pointing upward. L is pointing upward, B is pointing into the page, so the force will be pointing to the right side, And for the upper wire, the current is going to the right side, and L cross B pointing upward, so like this. And here, the current is going to the left side, so L cross B pointing downward. So actually, F2 and F3 should have the same magnitude and point to the opposite direction, so that they cancel each other. However, this F2, this F1, will point to the left side. So when you try to pull it to the right side, there will be a force pointing to the left side. So you need to do this work, to really pull this thing out. And actually, if you consider it quantitatively, and we have phi b to be b times a, and so we consider the width inside the magnetic field is x, and then of course this line is L, which will not change over time, and B is supposed to be a constant magnetic field, so phi b is a BLX. So now we consider the magnitude of the EMF, which will be like this. So we consider the magnitude, so we just ignore the negative sign. So so BLX is plugged in here, and then B and L won't change with time, so B and L can be put forward, and dxdt is the velocity. So we have BLV for here, in which we have replaced dxdt with v, so the speed at which the loop moves. So this is the electromotive force. Then suppose we don't have any battery. We actually don't have any battery, so the current would be nothing but E over the R, which is the total resistance of this loop. So I is BLV over R. So this is the induced current. Yeah, like this circuit diagram. So just now I already mentioned we will use the Lorentz force to consider the actual force F1, what F1 is. So F1 is ILB. So just now we already know that I is I is this one. I is this one, BLV over R. So we just plug in BLV over R here, so that F is BLV over R times LB. So we have L square and B square. B square L square times B over R. So we just gather the terms. Yeah. So this is actually the force. And finally, the work done, or actually the power will be Fv. The power will be Fv. The work is Fs, or generally F dot ds. So power is the derivative of P is dw dt. P is dw dt. So we have a ds dt, which is a v. So finally, the power is Fv. So we multiply an additional v here, so that we have b square L square v square over R. So actually, this then is appear as the thermal energy, which means when you pull out this, then there will be a force pulling backward. And then actually, after you pull it out, then there will be some heat generated through this loop. Okay, any questions? So here we discuss the so-called eddy current. The eddy current. Just now we mentioned that we have a loop. So that you know the current will going through the loop, which is obvious. But actually, even though you have a metal plate there, as you pull out a solid conducting plate out of the magnetic field, there will be eddy current. In Chinese, it is called So this is called the eddy current induced in the plate. A typical loop of eddy current is shown. So when you try to pull this metal plate out of the magnetic field, then there will be some current here. It don't really necessarily follow a specific path. It doesn't necessarily. It's just there will be just some current inside, going inside the plate. Yeah. So more generally, when we consider Faraday's law, we will write it like this. So originally on the left side, it is like E equals minus d phi b dt. Maybe we have an n factor there if we have multiple terms. Now we replace this E by the more general form as this line integral. So actually so in chapter 24, when you learn the electric potential, it is like V equals minus E dot ds. When you learn this one in chapter 24, at that time it's called the electrostatics, 静电学. So in that case, when you consider the E field without any magnetic field changing, then you can use the concept of electric potential. You can use the concept of electric potential, which means that suppose you have a point and then you're going like this, going back to this, then you integrate this E field over this path, then it no matter this how this path look like, then this integration should always be zero. However, here this is not zero anymore. This is like suppose we have a loop here. We have a loop here, and then just now just tell you that we have a magnetic bar, and then we put this part close to it. Then there will be a induced current going clockwise or counterclockwise, depend on whether it is a north pole or south pole, or moving closer and moving away. So in this case, there will be a current going, just say clockwise, which means there will be a electromotive force. So you cannot imagine this case using the concept of discrete voltage or discrete potential difference, because it's just like when you consider the potential at this point, and then you're going for the loop, it should be zero. And actually, when you consider there is some resistance here, and the current is going in this way, which means that the electric potential for this point should be higher than this point, and so as for point 1 should be higher than point 2, should be higher than point 3, should be higher than point 4, blah 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 blah, and then up to this point, it should be like this point N should be, the potential at point N should be higher than point 1, but it's not the case. It's just like you're going upstairs or goes upstairs, and then going for a loop, and then you go back to here. You're going back to here. So you cannot simply apply the electric potential for here, because this is not the electrostatics anymore. Electric potential is just a concept used in the electrostatics. So yeah, so induced electric field are produced not by static charge, but by changing magnetic flux. Therefore, electric potential has meaning only for electric field that are produced by electric charge. It has no meaning for electric field that are produced by induction. So it is somehow like this case. Yeah, there are some electromotive force, say like clockwise, and there will be current, but you cannot really consider what is the voltage at this point and voltage at that point. There will be some electromotive force pushing the current going clockwise. So in this case, on the left side, it is a closed line integral, or the loop line integral for the E field. So maybe we stop here and